Good evening, everyone. I'm Calvin Joseph, and I'm a research scholar from IIT Kanpur. And today I'll be conducting your week 2 problem solving and doubt clearing session for the course Digital Circuits taught by Dr. Santanu Chattopadhyay from IIT Kanpur. Okay. So, as the last, we also had a session last week where we had done, we introduced the subject, we had talked about number systems, etc. In this week, we will also continue a little bit more about number systems, but then we will focus on Boolean algebra as well. Okay, so this is the for this week, we'll be focusing on number systems and additionally Boolean algebra. Then, for certain information, so these videos are available on the Swayam portal. So you can log into your Swayam portal and from there you can see the videos. This is let me again just repeat this for everyone's understanding. So this is a UG core course. Okay, it's a 12-week course and you get 4 credit points for this course. The exam date is 24th October 2026. It's Sunday. It is on Saturday. All right. And the last date for exam registration is 14th August. Okay, so you make sure if you're planning to write the exam, get certified in this, you register for the exam. Okay, there's a domain, you get a domain certification in this course. There's also an announcement section on the Swayam portal where you'll get to know that when these doubt clearing sessions are going to take place or whether the videos are uploaded as well as whether the assignments are there, when is the assignment deadline and everything. Okay. Next, for the exam, as I said, the exam date is 24th October, Saturday. And if you register before 10th August, then the cost is 1,000 rupees. But if you register between 10th August to 14th August, between 5 p.m., you have to pay a little additional fees as well. Okay? So who can register for these courses? So there are students who are doing various programs in various colleges. For them, they have to take some NPTEL courses, some NPTEL credits they need. For them, it is there. Also, it can be used for faculty development program, where a faculty member can get certified that they have done this course. For that, they need to pay some additional small amount they have to pay. Okay, and if you do like 3, 4, or large number of NPTEL courses, and you can say if you come in the top 3 or you come the first, there are various categories. You can be an NPTEL star. There are various categories, and actually I met one guy who we had done lots of these NPTEL courses, and by virtue of doing many of these NPTEL courses, he could come to IIT Kharagpur for some project and for some training. Okay, so that is another way you could also get an access. You can improve your chances as well. Okay, so the exam marks, the total marks which will be there for your certificate, you'll have 25% from the assignment, and that is best of 8 from 12, and also 75% is from your exams. And the minimum criteria to get the certificate, that is, you have passed this, you have to get 10 out of 25 in the assignments, and in the exam, you should score at least 30 out of 75. Okay, the more you score, the better. And this is an easy subject, so you should try to get as high marks as possible. And you can also give me feedback. You can also ask me doubts. So the purpose of these sessions are so that whatever doubts you have, whatever queries you have, you can ask me, and I'll try my best to solve your doubts and questions. Okay. So the outline for today is we'll be talking regarding the introduction we have completed. We'll talk about number systems a little bit further regarding number systems. Then what is floating point representation and the various formats of floating point representation. Then we'll discuss about Boolean algebra, which is certain things which we use to analyze combinational digital circuits. Okay. Right. So any queries till here, or is it all fine? Okay. So right. So today is week 2. right? Week 2 for digital circuits. And you'll have to bear with my handwriting. It is not very great. Uh, so if you're not able to understand something, you can let me know. All right. Okay. So if you remember last class, can anyone tell me what you studied in last class last week? It would be good if the session is interactive. You can unmute and you can tell, or else you can also write a message, send a message. Both options are available.
Number system conversation,
Yes, yes,
octal
yes.
to hexa.
Okay, okay. Good, good. Yeah. So we had done last time various number systems. And the main number system which you need is you are aware of the decimal number system, but now you have to convert to binary number system. Okay. You have to go from decimal to binary. And then in binary, you can further make it into, octal, hexadecimal, and so on. Okay, you can make it into more difficult number systems as well. And these binary, octal, hexadecimal are very useful for us. But there are also, BCD number systems. BCD number systems is number systems related to 10, etc. But in terms of bits, in terms of a digital representation, etc. So there are various number systems. And in that, you also learned how to represent signed number systems and unsigned. Signed and unsigned numbers, as well as you also did fractions. Okay. So in signed number systems, you had studied what is known as ones complement and two's complement also you studied. Okay. So let us say you have a number 5. In binary, how do you represent the number 5? Positive 5, how do you represent? Can anyone tell?
101.
Yeah, you represent 101. Since we are also including negative numbers also, we write it as 0101. Okay, it's one's complement of this will become, what will be the one's complement of 5?
1010.
Yes, 1010. And then if you add 1 to it, you get the two's complement. Okay, that is 1101. So this is the two's complement. Two's complement of it. All right. So now let us take the number 12.125. How will you represent it in binary? Can anyone represent it and tell me? 12.125.
1100.01.
1100.01. 1. Is this correct? What do others think? Hmm? Okay. So actually, this is, let's go over it. So this is dash, 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 dash. So this is 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3. Your decimal point, then 2 raised to minus 1, 2 raised to minus 2, 2 raised to minus 3, 2 raised to minus 4, and so on. Right? So you know that 2 raised to 0 is 1, 2 raised to 1 is 2, 2 raised to 2 is 4, 2 raised to 3 is 8, 2 raised to minus 1 is 0.5, 2 raised to minus 2 is 0.25, 2 raised to minus 3 is 0.125, 2 raised to minus 4 is 0.0625. Okay, so what he told was 12 is correct, that is 1100 is correct. But if it is 0.125, it will be 001. Okay, 001. So it becomes 001. And then for the 0. Okay, so this is the number 12.125. Now, these are fixed point numbers. That is, you have told where is your decimal point is there. And your range is also fixed. Okay. But there is another type of numbers which is known as floating point numbers. Okay. There's another type which is known as floating point numbers. Okay. So what is this number? Let us say we have number 1, 2. Let us say we'll take 12. Okay. We take the number 12. Let me start easy example. Let me start with the number 16. Okay. This is the number 16. 16 is 16 also 16 into 10 raised to 0, right? 16 can also be written as 1.6 into 10. It can also be written as 0.16 into 10 raised to 2. It can be written as 0.016 into 10 raised to 3. Are all of it same or is there any mistake in it? They are a similar representation, right? That is 16 is 16 into 10 raised to 0. It is also 1.6 into 10. It is 0.16 into 100, 0.016 into 1000. 16 can also be written as 160 into 10 raised to minus 1, 1600 into 10 raised to minus 2, and so on. So basically what you're doing is that a decimal point that is floating, that is this point is here, this point is here, this point is here, this point is floating. Okay, it is floating. So let's see, we'll try to understand what is the power of this method, okay, how effective it can be. So we have this number 16. Okay, suppose we write it as 1.6 into 10 raised to 1. This is known as the mantissa. This is known as the exponent. And this is a plus, positive number. So this is known as the sign. Okay, this is known as the sign. Now, this is in terms of, decimal format, in terms of 10, 10, the binary, in terms of the number system 10. But we want it in terms of the binary number system. Okay, we want it in terms of the binary number system. So how do we write it? 16 is actually what? 1, 0, 0, 0. No, it is 1, 0, 0, 0, this. This is the number 16. Now, you can also write it as 0, 1, 0, 0, 0 into 2. Is there any mistake in this? Or is there any doubt in this or any questions? You could also write it as 0, 0, 1, 0, 0, 2 into 2 raised to 2. Basically, what you're doing a right shift. Right shift is basically you're dividing by 2. So to compensate, you multiply it by 2. Okay. This is done. Then you can also write it as 0, 0, 0, 0, 1 into 2 raised to 4. All of them are the same. So basically, what you're doing is your point which is there, you're floating it. And this is known as these are known as your exponents. Okay, these are known as your exponents. So we'll start with the basic 14-bit representation. Okay, 14-bit representation. So in the 14-bit representation, you have one bit. This is known as the sign bit. Then you have 5 bits. This is for your exponent. Then how many more bits do you have? So you have 5 plus 1, 6. 6 minus 14 is 8. So then you have another 8 bits. This is for your mantissa. Okay, this is for your mantissa. Okay. So now, how do we write? We want to have a unique number. We want to have a unique number for this. So your 16, which actually is 100,002, or actually it is 100,000.0002. Okay. This is your number. What we do, we shift it such that this thing that is before the point, that is 1. So for that, what do we have to do? We write it as 0,000,000, right? Into 2 raised to 1 shift, 2 shift, 3 shift, 4 shift, 2 raised to 4. Into 2 raised to 4. Okay. So this part, so this is 1.000. So now this 4, this becomes your exponent. 4 becomes your exponent. This part becomes your mantissa. And since it is a positive number, it's your sign bit will be 0. So you represent it as 0. Okay. And this is your sign bit. This is your sign bit. And your mantissa will be what? Mantissa is all 0. 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay. 8 zeros are there because these 3 zeros are there. You pad it, it will all be zeros. And this 4, this number 4, you have to add an offset. Okay. You have to add for 2 raised to 4. You have to add an offset of 16. Okay. You have to add an offset of 16. So you'll have to do 16 plus 4, that is equal to 20. No, you'll have to add an offset of 15, sorry. 15 plus 4, so that is 19. So 19, you have to convert it into binary. So that will be equal to 1 and 1, 0, 0, 1. Okay, so this is your number. So this is actually your 19. This is your mantissa. And this is because there is an offset. So this is known as your offset. All right. Okay, any doubts in this? I'll do one more example because this is difficult. It will take a bit of time for you to understand. But if there's any doubt, you ask me, or else we'll go to a little bit more better example so that you can understand it better. Any queries here?
So why you have add to 15 plus 4?
Okay. So 4 till 4 is fine, right? Till 4 is fine. Now, if you want to have, negative exponents, you cannot represent it. So to have those negative exponents, what do? We, to have those negative exponents, we add an offset of 15. So I'll come to that example later. So let me try once more. Let me explain it once more to you guys. Okay. Okay. Yes. So let me take a different number. A different number I'll take to make it more better for you guys. So let us take, we have the number 13. We have the number 13. So number 13, you represent it as 8401. So that is 1101.000 in binary. Okay. 13 is 1101.000 in binary. Now, floating point should not be like, you can't keep on changing it, floating point, this point, that point, that point. Then everyone will get confused. What is the proper exact representation, which is the standardized representation? So for that, what do we do is we will shift. We will shift such that you will have here all 000 and you just have a 1 over here. Okay. You have to do left shift, right shift, something, or you have to do, but you have to make it in this format. Okay. So to make this number into this format, what do you have to do? You have to write over here this one has come over here. So now this one will come here. So this is 1, then you have 0, then you have 1, and then all these zeros come. So it becomes 0, 0, 0. Okay. It becomes, all these come and it becomes 0. Now, what you have done, how many decimal points you have gone from 1 here, 2 here, 3 here. So that's why you have to multiply it by 2 raised to 3 into 2 raised to 3. Okay. So in this one step, does anyone have query? You can ask me. I can repeat it again because this is very important. Okay, let me repeat again for everyone's understanding. It may be slow, but I'll repeat it again because floating point number system is it's a bit challenging to understand. It is not very easy and simple as normal number systems are for most people. Okay. So 13 is there. 13 in terms of binary. Normal binary is 1101.0002. But now if you want to represent in terms of the standard IEEE floating point representation, what we have to do, all these should be 0 and here it should be 1. It should be 1. So what I do, I have to do right shift. I have to do right shift. So it becomes what? 1.101 and rest all zeros gets added. Okay, rest all zeros are there, it gets shifted. Okay, but since I have shifted it by 3, I have to do into 2 raised to 3. Okay, I have to do 2 raised to 3. All right. And okay, to make it more better for you guys to understand, this number, that is this number is what? It is 1, which stands for this, plus this is for 0.5, and this is what? Plus 0.25. Right? This number is, sorry, plus 0.125, plus 0.125. Okay, and this number is what? This number is 8. So this number becomes actually equal to 1.625 into 8. So can anyone do 1.625 into 8 and tell me what is the value? Okay, are you guys all able to hear the video and the audio? Is anyone facing an issue?
No, sir.
Okay, very good. Okay. So can you tell me what is 1.625 into 8?
13.
13, right? So this is equal to 13. So that's what. So I just want you guys to be confident to understand what exactly I am doing. If I am shifting the bits to the right, I have to multiply it accordingly with the number of how many times I'm shifting it right? So I've shifted it 3 bits right, so I multiplied by 2 raised to 3. Okay. And then if you actually do the exact
Sir,
value, yes.
is this IEEE format?
Yes.
Okay, sir.
This is based on the IEEE format I'm doing. Okay, so it becomes 1.101000 into 2 raised to 3. So this is the number which we need. So now, what is the main information which we want now is, we are concerned with this information. We are concerned with this information and with this information. Okay. So now, what is our sign? Our sign is positive. So our sign bit will be 0. Okay. What is our exponent? Well, let us start with the mantissa. What is our mantissa? Mantissa is whatever is after the decimal point. So that is equal to 101000. Okay. And what is our exponent? Our exponent is 3. It is currently 3. Now, in this IEEE format, what they do, they add what is known as a bias. Bias means you add something positive. Okay. So, Saujanya, please don't write anything here. So, you add something positive. So, how much you add positive in the 14-bit representation? You add actually plus 15. Okay, you add plus 15. So what is, so you tell me what is your new exponent. Your new exponent will be equal to 3 plus 15. So 3 plus 15 is what? It is 18. Okay. 3 plus 15 becomes 18. Any queries still here? Any doubts? Okay. Now, 18 has to be represented in binary. How do you represent 18 in binary? It is actually equal to,
Sir,
okay. Yes, yes, yes.
sir, we have to add 15 for a new exponent, na?
Yeah, yeah, yeah.
So, what is the use of that new exponent? How,
Okay.
why?
Okay, okay, okay. Yes, yes. So over here, if you see, exponent is what? It is some 2 raised to x. Okay, it is 2 raised to x. Now this x, in some numbers, x could be negative. X could be less than 0. But in your exponent bits, which is only 5 bits, you cannot represent negative numbers. So for that case, what do? We add a bias. Okay, we add a bias. So for that bias, the bias which we add is, this is 5 bits, right? So the bias which we have to add is 2 raised to 5 minus 1 and minus 1. So that becomes equal to 2 raised to 4 minus 1. So that is 16 minus 1, that is equal to 15. Okay. That's why I have to add this bias. So I'll show an example when the need for the bias becomes understandable for you guys. But now you just assume that we add a bias of 15 in this representation. Okay.
Sir, but in normal
Mm.
class, we have to add 16.
Which one you
Bias
said?
16 we have to add.
Oh, no, because
In PDF, it should be 16.
yeah, yeah, that was not IEEE standard. That was the one standard sir was using. Let me show you. Oh, see, when you go for the IEEE format, it is like this. You have total bits of 14, 1 bit for sign, 5 bits for exponent with a bias of 15. Okay. So for the
Okay, okay,
IEEE
okay.
format. Okay. The one which sir used was an example for you guys to become easy for you guys. But here I'm using the IEEE format one, so it's the bias of 15. Okay. Right.
Sir,
Yes.
in normal class, my sir told 127 is added.
Yeah. See, there is this confusion of bias. Let me finish it off now only. So bias is dependent on your format. Okay. So one is the 14-bit format. 14-bit format is there. And you have what is known as the number of bits. Number of bits for exponent is 5. So if the number of bits for exponent is 5, then the bias which you need to add is 2 raised to 5 minus 1 minus 1. Okay, please remove this. Whoever has written this, kindly remove this. Who has made this diagram? Because it's not going from the screen. Let me stop sharing once. Okay. So in this case, 2 raised to 5 minus 1 is 2 raised to 4. And 2 raised to 4 is 16 minus 1. So that is equal to 15. Okay. In the next case is the 32-bit format, which is actually your single, data type. So for this data type, let me just check 1 minute. written it somewhere. Yeah. For that, you use an 8-bit exponent. Okay, for that, you use an 8-bit exponent. And because you use an 8-bit exponent, the bias will be 2 raised to 7 minus 1, that is equal to 127. Okay. And if you use a 64-bit format, which is your data type double, then the number of bits in the exponent is 11. That's why this is 2 raised to 10 minus 1. So that is equal to 1023 bias. Does this clear the confusion?
Yes, sir.
Okay. So that's why the bias is something which is standardized. So if a 14-bit format, you have to add a bias of 15. 32-bit format, which is single data type, there the number of bits is 8 in the exponent. And so you have to add a bias of 127. And in the case of a double data type, which is 64-bit format, the number of bits for the exponent is 11. So the number of bits in the, so the bias which you need to add is 2 raised to 10 minus 1, that is 1023. Okay. So this confusion will be there. So I've written it for you. So later on, after the video is there, after it's all done, these notes I will upload on the drive. So you can access it from the drive as well. Okay. Okay, so let's get back to our thing. We found that a new exponent, that is the one where we added the bias, that comes out to be 18. And to represent 18, we represent it as 10010. Okay. This is actually equal to your 18. Okay. So now your bits will actually be 0. And then your exponent, that is 10010. Then your mantissa. This is known as your mantissa. So your mantissa will be equal to, what is this? 101000. Okay, so it is what? 101, 101, and then 3 zeros. That is, you have your 000. And then since it is 8-bit, you can add additional zeros. Okay, so this is 8-bit. Okay. Okay, so I know you will all have lots of doubts. I have not explained it very well. So please, I'll try one more example so it will make more sense for you guys, right? So let us start with an example that is 0.125. Okay, 0.125. 0.125, when you represent it in binary, what it becomes? Or let me try a number which has more bits. Let us say 0.125 plus 25. Okay, let's start with 0.375. This is 0.375. When you do it in binary, what it becomes? It becomes 0.011. Okay, this is in binary. 0.375 in decimal becomes 0.011 in binary. Now we have to make it into the standardized form. So in standardized form, what do we have to do? We have to make it what? All this should be 0 and 1. 0 and 1 should be there. So what we have to do? We have to shift this 1 bit here, and then this bit will come here. So it becomes 1.10. Okay. This is how you represent it into 2 raised to, you have shifted it by how many bits? You have shifted it by 2 bits, but you have shifted it towards the left. So this becomes 2 raised to minus 2. Okay, it becomes 2 raised to minus 2. Okay. Now you tell me what is the sign. Sign is positive. So the sign bit is 0. What is your mantissa? Your mantissa is 100. Okay, this is your mantissa. What is your exponent? Your exponent is minus 2. Then you have to add exponent with bias. Your exponent with bias becomes what? Becomes minus 2 plus 15. So that becomes equal to 13. Okay. Now you have to represent it in the floating point. In floating point, what you have? You have a sign bit. Then you have your exponent. And then you have your mantissa. So sign bit is what? 0. Exponent is 13. 13 in binary, how do you get it as? 1, 0. Then you have 1, 1, and you have 0. Okay, 8 plus 4, 12, plus 1, 13. And your mantissa is what? It is 1, 0, 0. And then remaining all you are empty, so you put it all as 0, 0, 0. So this is how you represent. This is the floating point representation of 0.375. Okay. Any questions? Let's try some sums. Sums will probably improve your understanding better. Let us take a. Let me take an easy sum for you guys. Let us try this. Is someone saying something?
Yes, sir. Once again, then bias concept.
Actually, could you repeat again? I couldn't hear properly. Or you could send in the chat.
Sir,
Tell.
once again, explain bias concept.
Okay, bias concept. Okay. So, first of all, bias is added when we have to deal with negative exponents. Okay, that's why I specifically took this example where you have 2 raised to minus 2. Your exponent is negative. So if you have a negative exponent, to represent it in your floating point is not allowed. So because you cannot represent a negative exponent, what do? We add a bias. Okay, so you have an exponent over here is minus 2. And as per the format, we have to add a bias of plus 15. So we add an exponent with a bias. So it's minus 2 plus 15, that is equal to 13. Okay. So that is the concept of bias. And how much of bias we need to add, that comes from here. In a 14-bit format, where the number of bits for exponent is 5, the bias required is 15. In a 32-bit format, when the number of bits for exponent is 8, the bias required is 127. And in a 64-bit format, when the number of bits for exponent is 11, the bias required is 1023. Okay.
Okay, sir. Thank you, sir.
Okay. Okay, so let me start with the sum, which is easy. So more and more as you solve sums, more and more you can understand. Okay, kindly don't write anything on the screen. Okay, let us try this one. We have given the following 32-bit binary number in IEEE 754 single precision format. What is this value? Okay, let us see. So how do I paste it here? Okay. So this is the number. Okay, Simran Singh, kindly please don't add your tick marks, everything. Yeah. So this is a number in IEEE format. This is your 0. This is your sign bit. This is your exponent. And this is your mantissa. Okay, this is your sign bit, exponent, and mantissa. So your sign bit is 0 means is the number positive or negative? Can anyone tell me? Sign bit 0 means number is positive or negative?
Positive.
Okay, very good.
Positive, sir.
Very good. So,
Positive.
yes, so it is positive. Very good. Now in the exponent, if you see the exponent, right? Can you tell me what is the numeric value of that exponent? It is having 1 and then 1, 2, 3, 4, 5, 6, 6 zeros and 1. So can you tell me what is its decimal equivalent?
1, 2, 3, 4.
So,
127. నుంచి రివ్యూ ఐ మీన్
yes.
ఈ వాల్యూ ఎంత చెప్పు.
No, you just tell me what is the decimal equivalent of 1 triple 6 zeros and 1.
129.
Yes, very good. So exponent,
129.
very good. Exponent with the bias is 129. Okay, very nice. Now I want to remove the bias. So exponent without the bias, that is 129 minus 127, as she was saying. So 129 minus 127 is how much?
2, sir.
2.
Exponential.
So your exponent is 2.
2.
Okay. Okay. So till here, is there any doubt till here? So we have found out what is the sign of the floating point number. We have also found out what is the exponent also. So till here, there's no doubt. I'll proceed with the mantissa. Okay. Now in the mantissa, if you observe, like all this is 0, 0, 0, 0, 0. They don't have any effect, right? It is there for precision, but currently, since we are trying to learn the concept, okay, we are we are just having it. Okay, so Konda Richita, because it is in the single bit format, this is in the single format. Okay, that's why we have to subtract it with the bias of 127. Since it is in the single format, we have to subtract it with the bias of 127. Okay, so now in the mantissa, okay, what do you mean by 19? What do you mean by 19? It is 129. Lohit, you were saying how is it 19? For what it is 19? Oh yeah, 129. 129 because this is 2 raised to 8 is 128. And then, no, 2 raised to 7 or something. What is that?
2 power of 7.
2 power 7 is 128 and then plus 1. Yeah. Okay, okay. Okay, so let us check that also. So let us see. You have 1, 666 zeros and 1. So this is 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, 2 raised to 4, 2 raised to 5, 2 raised to 6, 2 raised to 7. Okay, 2 raised to 7 is what? 128. And this is 1.
28.
Okay, so that's why 128 plus 1, it becomes 129. Okay, Vivo, please kindly don't add something. Okay. Okay, so you got it 129. Now, we have to subtract bias.
Add 1.
So when you subtract bias, what it come? 129 minus 127. So it becomes 002. Okay, so that is your exponent without bias. Now for your mantissa is this part, right? If you can see, this is your mantissa part, right? So your mantissa actually is 1.0 and whatever is there, 1.01101. So it is 1.01101. So this is your actual mantissa. Okay, this is your mantissa. And you got your exponent is 2, right? Your exponent is 2. So your number, what is your number? Your number is 1.01101 and it is positive and into 2 raised to 2. Okay. So can you do this calculation? What is this number? To simplify, what we can do is we can, you calculate what is this number. What does this number mean? So let us do it. So let us say this is 1.01101. So this is 2 raised to 0. This is 2 raised to minus 1, 2 raised to minus 2, 2 raised to minus 3, 2 raised to minus 4, 2 raised to minus 5. So this is actually equal to 1 plus 2 raised to minus 2 is what? 0.25. 2 raised to minus 3 is what? 0.125. 2 raised to minus 4 is 0.0625 and 2 raised to minus 5 is 0.03125. Okay. So it becomes 5, 2, and then 6, And this becomes 5 plus 7 plus 3, so 10, 0, 1, 4. So it becomes 1.40625. Okay. So this is what? So this is equivalent to 1.40625. And this is you're multiplying by 4. So how much is this? 1.40625 into 4?
1.625.
No. 1.40625 into 4.
1.625.
How? It should be
1.4065 into 4.
5.625.
Yes.
5.625.
5.6.
Okay, correct. 5.625.
Okay, yeah.
Yeah. That's why I was so shocked actually. Fine. Okay. Okay, so very good. Konda Richita, I have not understood your question. Oh, Mantissa part. Okay. So Mantissa part is very long, but all are remaining zeros, so they can be ignored. So they are ignored. Okay. And so we have 0, 1, 1, 0, 1, but in the actual format, what it means is 1.01101. Okay. Yes. Okay, someone is writing on the screen. Please don't write. Okay. So we'll start with some questions. Let's start with, okay, Aishwarya CL, kindly please remove your annotation. Thank you. Okay. Let's start with this question. 32-bit IEEE 754 single precision floating point binary representation of the decimal number 23. Okay, we have the number 23. You have to represent it in floating point binary. Okay, so let us start. We have the number, question 1, we have the number 23. So first, what is the first step? You have to represent it in terms of, you take it from decimal to binary. So 23, how do you write 23? 23 will be 16 plus 16 plus 7. So 4, 2, 1. Right? So this is your 23. Is this correct? 1,
Yeah.
0, 1. Okay, so this is your 23. Now, 23 has to be converted into and this actually is, let me say, 0.00. This is in binary. Now I have to do right shift, right? Because what I need 0, 0 here, and then I need 1 over here, and then I need to continue, right? So what I do a right shift of 4 bits. So it becomes 001.011100. Okay. And since I've shifted it by 4 bits, I multiplied by 2 raised to 4. 2 raised to 4. I've done a right shift, so I add 2 raised to 4. So this is your step. This is your step. Okay, now let us start with what is the sign bit. Sign bit is simple, it is positive, so your sign bit will be 0. What is your mantissa? Your mantissa is what? The 0, 1, 1 part. Okay. What is your exponent? Your exponent is 4. Now, you need to add the bias. You need to add the bias. So you need to add exponent with bias. So what is your exponent with bias? It should be 4 plus 127. 4 plus 127 is how much? Okay. Kindly mute yourself if you're not talking, if you're not answering the questions. Okay. So yeah, previous week there was a class that was recorded and it's available on YouTube. Okay, it's available on YouTube. So the exponent with bias becomes equal to 131. Now is a very challenging thing. How do you represent 131 in binary? You need to represent it in this 8 bits, 131. How do you represent? Can anyone tell me what is the representation of 131 in binary? Okay.
1 0 0 0 0 1 1.
Okay, very good. Thank you. So it is 1 0 0 0 0 0 1 1. Okay, very nice. So you guys are quite fast. Very good. So now we will have to write the overall number. We'll write the overall number. Overall number is what? It is 0. This is for the sign bit. Then the exponent is, as you have told, it is 1 0 0 0 0. One more 0 1 1. And then you have the mantissa part, which is this part. Okay. Mantissa part is 0 1 1 1 0 0. And then it goes on with 0. Okay. It goes on with 0. So is this clear? Or you want me to repeat it once more?
Yeah, same or written. There was the sheet open చేస్తా sheet అది అయిపోయి నాకు పెట్టారు ఇదే కదా ఎయిర్ఫోన్ ఓకే
Okay, kindly. Okay. So let me repeat it once more for everyone.
One doubt, sir.
Okay, tell what's your doubt?
In some, yes, sir. And in some cases, we are subtracting it, sir.
Yes. Okay. Okay.
How we are doing it, sir?
When we are converting it from, yes, I understood your doubt. You are asking in some places we are subtracting, in some places we are adding. Why is that the case?
Yes, sir.
When we are going from the number 23, which is in decimal format, to the floating point, then we have to do the what you say? We have to add the bias. We are going from the floating point number back to our actual decimal number, then we have to subtract. Okay. I hope that's clear.
For number conversion, we need to do it, sir.
Yeah. Like, see, when you are going from, let me go to next page moment. When you are going from decimal to floating point, when you're doing that, then you need to add bias. But when you're going from the floating point representation to decimal, then you have to subtract the bias. Okay. Right? Okay, someone wanted to see the question. The question is here. This is your question. Okay. So let us start with the Boolean algebra, otherwise we'll not be able to complete the topic. We'll also do some part of Boolean algebra. If we have time, we can revisit the floating point numbers as well again. Okay. So we'll start with Boolean algebra, where you have 1 minute. Okay, you have Boolean algebra now. In Boolean algebra, let me check what was supposed to be taught. Logic gates, truth table, SOP, POS. Okay. Okay. So in Boolean algebra, you have various logic gates. Can you tell me some common logic gates which you all know, which you all are familiar with?
And or, and or, not.
Not and or and nor
Exclusive
XOR
OR gate,
XOR.
exclusive OR gate.
Yeah, or X or X nor
XNOR.
Okay, okay, very good. And or
XOR.
okay,
not
not okay. So all of these gates have a truth table.
exclusive gates.
No, exclusive gates, X or X not. Okay. So let us say we have AND gate.
And nor.
Yes.
Yes, sir.
This is a representation of AND gate. You have input A, B, right?
Yes,
So
sir.
now, and this is your output Y. So what is the truth table of this? 0, 0,
Yes,
0,
sir.
1, 1, 0, 1, 1. What is the truth table of this?
0001.
0001.
0001.
Okay, very
Both.
now let us say what gate is this?
NOR gate.
XOR gate.
XOR gate, XOR gate.
XOR gate.
A, B, Y.
XOR gate.
Correct, correct. It's XOR gate. Okay. So the, again,
Same input,
0,
output
0.
0.
Okay. Same input, output is 0. Okay. For 0, 1, what will it be
Different
then?
input,
Yes, sir.
output 1.
Okay. 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 So one minute. So I'll just share the link. Let me share with,
0.
yeah, 0, 1, 1, 0. Okay. Let me share. So have you got the YouTube link? So have you shared the
Yes,
YouTube
sir.
link? So in this channel, under the playlist of digital circuits, the first video has come. And then after this meeting, it will be processed everything. And the second video also will be uploaded soon. Okay. Okay. So this is the truth table of a XOR gate, right? Now, this Y equal to A XOR B, it has a Boolean expression, which actually is A and B bar plus B and A
A
bar,
bar.
right?
A bar.
This is the Boolean expression. So how do we know this is the Boolean expression? So let us say you have A, B, then you have A bar, B bar, then you have A and B bar, then you have B and A bar, and then finally you have A and B bar, or of B and A bar. Okay, let us write it. So this is 0, 0, 0, 1, 1, 0, 1, 1. A bar is the opposite of A, that is 1, 1, 0, 0. What is B bar?
1010.
101.
1 0.
1, 0, right?
1 0.
Yeah, then A and B bar is what?
A 0.
0100.
1.
0, 0, 1, 0.
0010.
1, 0. Okay, and what is B and A bar?
0, 1, 0,
0, 1, 0, 0. Right? And what is A and B bar plus B and A bar?
0, 1, 1, 0.
0 1.
1, 0. Okay, so that is how truth table we can identify whether they are the same or they are not. Okay, whether they are same or not. So let us see what questions are there. Min term, max term. Okay. Hmm. All right, all right. So next, let us see some Boolean algebra. You guys should know it. So you please tell me what is this. A and B plus C is actually equal to what?
A plus AB plus AC.
Okay, very good. Then what is A and A equal to?
A.
A.
Okay.
Zero.
Okay, what is A and 0 equal to?
0.
Zero.
Okay, what is A and 1 equal to?
A.
Very, no, A and 1 is A. Okay. What is
Yes.
A or 0 equal to?
A.
A.
Zero.
What is A or 1
A
equal to?
plus 1 A. A.
No,
One.
A plus 1 is 1. Okay.
1.
Because if you, in your OR gate, if
1.
any is 1, your output is 1. So that's why A or 1 is 1. In your AND gate, if any
Yes.
0, your output of your AND gate is 0. That's why A and 0 is 0. Okay. These are
Yes, sir.
important. Now, I have A bar. And again, I take the complement of A bar. What will that be equal to?
A.
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 Suppose I have A or B, their whole bar. What is that equal to?
Bar plus B bar.
A bar dot B bar.
A bar dot B bar.
Correct.
A bar
Dot B bar.
D Moivre's theorem. Okay.
Yes, sir.
Okay, very good. So now, suppose you have something like AB plus AB bar C plus A bar BC. This is some expression. They tell you you have to simplify it or something. Like that, they can ask you a question. Then how will you simplify this? Is it possible to simplify this?
C
Yes, sir.
common ತಗೋ.
B.
No,
B plus B bar equal to 1.
But where is B plus B
no, we
bar?
cannot simplify it.
Okay.
A B bar plus
A.
A bar equal to
Okay, I think this expression cannot be simplified. So let
Yes,
us.
sir.
Second and third may be simplified.
Sorry.
AB plus A XOR B into C.
AB plus A XOR.
A XOR B.
Okay, it is actually, you're saying it is AB plus A XOR B into C. Okay, yeah, that is one way. Correct. That also is one representation. Let us go to a question where, so that I'm not asking you to do something difficult. Okay. Let's start with this one. Let's start with this expression. FABC is AB bar C plus
ABC
bar plus ABC plus AB bar C bar. Okay, let me write it down. F is equal to AB bar C plus ABC bar plus
plus ABC. ABC.
okay plus ABC plus
A B bar C bar.
A B bar C bar.
okay, thank you. So now you have to simplify it. How will you simplify it?
First, A common.
Okay, A is common for
A.
everything.
A. Answer A.
B XOR C.
Answer is A.
Okay, somebody
A
say
common.
A. Okay, yeah, let us
Sir,
try.
A B bar and A B got common, sir.
Okay.
Answer is A, sir.
Okay, answer say you guys are very smart. I'm not as smart. I'm not as quick. Let's go with a slower way. Okay, so you see AB is
A common.
common over here. And you also have AB bar here and AB bar is common here. So you can write what? You can write AB bar here. And whatever is AB bar common, it is what? C plus C bar.
C plus C bar.
Okay, and you also have AB common here. And then again you have C bar plus C, right? So what is C plus C bar?
1.
1.
Very good. So it is AB bar and 1. And you have AB and again you have 1. Okay.
1.
So
Yes,
becomes
sir.
AB bar
And
plus
A common.
now A
AB.
is again common. So you have
B
A,
plus B bar.
B
B
plus
plus
B
B
bar.
bar is 1. Answer is
A.
A.
Answer A.
yes, very good. Okay, so that's why the answer is A. So you have used some simple Boolean expressions, you have simplified it. So from a big, large expression, you have got it into a simplified expression. So is doing this useful or not? Should we do it or not?
Yes, sir.
Like the advantage which you
Yes.
get is you can use a smaller number of logic gates to implement a function. That is, if you need to use 10, 20 logic gates, if you can simplify it and get only to implement it in 3, 4 logic gates, that could be a very good case. You can save, circuits and all that. So that's why Boolean, simplification is useful. Okay. Let's do another question. Let us try this question. AB plus ABC plus ABD plus E. Can you do it and tell me what is the answer?
A.
Answer is
AB.
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 Answer is AB. Answer is AB.
Okay. I'm getting lots of answers. So
AB, sir.
AB, okay. Yes, it is AB. So AB is common. And when you take AB common, it becomes 1 plus C plus D plus E. And if you have 1 plus anything, all the other things you ignore. It becomes 1 only.
1.
So it is AB
Yes, sir.
into. Okay. Okay. Very good. Now, how many distinct Boolean functions can be formed using 4 input variables? That is, you have A, B, C, and D. So how many type of functions you can get?
16.
16.
Okay, very nice. What about others?
It's 2 power 16, sir.
2 power 16. Very good.
2.
Yeah. So why 2 power 16? Who said that and why?
Option D.
Okay, option. Okay. All right. So yeah, the correct answer is 2 power 16. So you have 4 inputs, right?
నీకు అవ్వదురా
Kindly, if you're not
నెక్స్ట్ టైం
okay. So if let us take a 2 input case. 2 input case is what? You have A and B and you have Y. So you have 0, 0, 0, 1, 1, 0, 1, 1. Okay. So now how many function outputs you can get? This could be 0 or 1. 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 So that is 2, 2, 2, 2. So it is what? 2 into 2 raised to 2. So that is 2 into 2 raised to 2. Am I right? No. No, 2 raised to 4. 2 raised to 4, right? So it is actually equal to 2 into 2 into 2. So it is 2 into 2 into 2 into 2. So it is 2 raised to 4. That is 16 of functions you can get for 2 input case. In a 3 input case, what do you have? You have A, B, C, and Y. And there you have like this 0, 0, 0, 0, 0, 1, 0, 1, 0. Like that you have
2
till
power 8.
okay. So that way you have 8 options. You have 8
2 power
options.
8.
No. It's not 2 power 8. It's not 2 power 8.
2 power 3.
Wait. Let's see. This could be 0 or 1. This could be 0 or 1. This could be 0 or 1. Go on. This could be 0 or 1. So you will have 2. 2 power 3 is your 8. Right? And then 2 power 3 is 8. And this could be 2, 2, 2, 2, 2, 2. Correct. It's 2 power 8 only. Sorry, it is 2 power 8. Admit.
Yes, sir.
Yeah. It is 2 power 8. So actually, that is actually 2 into 2 raised to 3. 2 into 2 raised to 2 raised to 3. That is 2 power 8. So that's why 2 power 8 is how much? It is 256, right? 256.
Sir.
So when you go for a 4 input case, it becomes equal to 2 raised to 2 raised to 4. So that becomes equal to 2 raised to 16. Okay. So that gives the number 65,536. Okay. So any queries still here? Okay, so let's go to the next. Tell.
Yes, can you please say the answer for the previous question, sir?
65,536.
No, sir. Actually, minimization of Boolean expressions, sir. That previous
Oh,
problem.
this one, AB plus ABC plus
Yes,
AB.
sir. Answer alone.
Answer is AB.
Okay, thank you, sir.
Okay. Okay. So next, we'll also study something. There's something known as SOP, that is known as sum of products. And there's something known as POS, that is product of
Sums.
sum. Okay. Let us say you have 3 inputs, A, B, C, and you have an output Y. Your truth table is what? Okay.
0 0
0 0 0 0 1 0 1 0
0 1 0 0 1 1 1 0 0
1 0 1
1 0 1
1 1 0
1
and
1 0
1 1.
1 1.
Yes. Now, this is like, so now if you have this, right? There can be some 1 0, all those can be there. So this is your minterm M0. Your minterm M0 is what? A bar and B bar and C
B
bar.
bar, C bar.
Okay, this is your
M1.
minterm M0, which corresponds to this. Minterm 1 is what? A bar and
A
B
bar, B bar, C.
and C.
C.
Okay, M2 is what? A
A bar, B, C.
A
B,
bar,
C bar.
A bar
A,
and C bar.
B, C bar.
Okay, correct.
M3 equal to
Okay, yeah, this sum of products I'm telling. M3 is A
A
bar
A
bar,
bar,
and
B,
B
C.
and
B,
C.
C.
yeah. So wherever is
M,
1 is there,
M4,
one is
What?
there, it is no bar is there. Wherever 0 is there, bar is there. For sum of products. Okay, for M4 is what? A and
A, B, B bar,
B
C
bar
bar.
and C bar. M5 is A and
A,
bar
B
and
bar, C.
C bar.
okay. M6 is what? A
A,
and
B, C bar.
bar.
B, C
M,
bar.
okay. M7 is what?
A,
A, B,
A
A,
and
B,
B,
C.
C. Okay. All right. So thank you. So now these are your min terms. So if your y output y is, suppose let us say it is 1, 1, 1. All the rest are zeros. So you can represent y. It is the summation of the min terms. What min terms? Min term 0, comma,
1,
4, 6.
0, 4 and 6. Okay. Yes, y is the summation of min terms 0, 4 and 6. And its actual expression is what? It is A bar and B bar and C bar plus A and B bar and C bar plus A and B and C bar. Okay. Any queries in this? Okay. All right. Now, could this expression be simplified? Can this expression be simplified?
Yes, sir.
Okay. What is the simplified expression? It is a bar plus a and b bar and c bar plus a b c bar.
B,
So that is actually b
B
bar
bar,
and plus a b and c bar. Right?
C bar common. C bar common.
Yeah. C bar, you don't get anything much out of it, right? You get b bar or a b and c bar. Okay.
B bar B.
Distributive law.
Okay. What is distributive law?
B bar A plus B bar.
Sorry, you are saying b bar a
A plus
huh,
B bar.
Huh?
plus
No.
b.
Sir, wrong,
Sir,
sir.
B bar plus A, sir.
Okay. I'm not
So
sure.
B bar plus C.
Again, repeat.
B bar plus A, sir. Into C bar.
Okay. So this is b bar plus a into c bar. Okay. So
Yes,
this is
sir.
some way you can simplify it. So the main thing is this one. This is your sum of products. Okay. Now, if this was 1 0 0 0 1 0 0 0 1 0, okay. In terms of sum of products, it is equal to summation M046. But in the term of min terms, in terms of product of sums, in terms of product
The
of sums,
complement of minterms, sir.
yes. So it will be 1, 2, 3, 5, and 7.
5, 7.
Okay. Now, it is the complement of your, so max terms are your complement of your min terms, right? So let us check
Yes, sir.
this example. Okay, let's see this example. Function x comma y comma z is summation of it is summation of 1, 2, 4, and 6, right? So, okay. If you're not actually actively answering, kindly mute yourself. Okay.
Okay, sir.
So, summation of m 2, 4, 6. But the options, it is in terms of product of sums. So in product of sums, what it becomes? It becomes
0, 3, 5, 7.
0, 3,
3,
5.
5, 7.
Okay. Now, 0 actually is what? It is actually
0,
A or B or C. Oh, sorry. Let us say in here it is actually X or Y or Z. So it is X or Y or Z. Okay. And 3 is what? It is actually equal to 3
X plus
X
Y bar
bar,
plus Z bar.
plus Y bar.
Y bar plus Z bar.
5 is what? X bar plus Y plus Z bar.
Y plus Z bar.
Z.
And 7 is what? X bar
X
plus.
bar plus Y bar plus Z bar.
Okay. Very good. So now, how does this happen? So if you have X and Y, if you have X bar and Y bar and Z bar, this is what? Your min term 0. And this is actually your max term 7. And your max term 7 is what? X plus Y plus Z bar. Okay? It is X plus Y plus Z bar. This is your max term. Seven. Right? And so if this is 1, this, okay, this will be M7 bar, and this is actually equal to 1. So your M7, this is equal to your X plus Y plus Z. No, there's a mistake here. Wait a minute. I'm
Sir,
confused.
for max terms, 0 is X bar
Sir,
plus Y bar plus Z bar. I think so, sir.
Repeat again.
Because means for max terms, X plus Y plus Z you wrote for 0, no, sir.
Yes, yes, yes.
I think so. It is X bar plus Y bar plus Z bar.
Okay.
Max terms it will be reverse.
Yeah, it is reverse, but I'm actually a bit confused. Okay, this let us keep for. Okay. What is clear is if you have, okay, let's write summation of M. Let us say we'll go for a 2-input case. 2-input case, that is you have A and B. The maximum, min term, let us say 0, 1, 2. Okay. So this is what equal to A bar and B bar plus A bar and B plus A and B bar. Okay. This is actually equal to your product of 3. So that is what? A bar and or B plus A and B. So that is equal to A bar plus A and B bar. And that gets
A plus A bar.
that actually becomes equal to your A bar plus B, right?
A bar plus B.
B bar.
Yeah, A bar plus B bar. Okay. So your and this is multiplied by nothing else because all of them are not there, right? So it is A bar plus, so this is sum, and this would have been your product, but that is currently not there. Okay. So let us check this question also. If x equal to 1 in the logic equation, then what will be this? Okay, so assume you put x equal to 1 in here. Then what will be the output here? What is the relation between y and z? Question number 14. Can you guys see it?
Yes, sir.
Okay, so suppose x is equal to 1 and your output is 1. So what is the expression here? Okay, so let me write the expression first here. Let me write it down. Question expression is x plus z into y bar plus z plus y bar plus z bar plus xy. Okay, z bar plus z bar plus x y bar. This is one expression. The other expression is what? X bar plus z bar into x plus y. This is equal to 1, right? Okay, this is your function. Your function is equal to 1, and this is the case when x equal to 1. So if x equal to 1, what can we simplify? This entire thing will become 1. Is it right?
Yes, sir.
Yes.
This will become 1 because 1 plus anything is 1. And this is what? 0 plus z bar into 1 plus y. Right? So what does this become?
Z equal to 0. Maybe, sir.
Sir, 0 plus y, sir.
What? Someone was saying something? So it is 1 and z bar is 0. So that means your z should be equal to 1. Okay, your z should be equal to 1. So let us start with this question also. Let me take it over here. That will be easy.
Sir, in the previous question, z bar
Z
equals to
equal
1,
to
sir.
0,
Z
sir.
equal to 0, sir.
0, sir.
Z bar equals to 1, sir. So
Sorry.
z equal
There
to
is 1,
0.
sir.
Okay,
You wrote
okay,
0
sorry.
there.
Yeah. Thank you for. So z bar is equal to 1. That means z is equal to 0. Very good. Yeah.
Explain once again, sir.
Okay, so now
Yes,
you
sir.
have x equal to 1. Okay, if I have x equal to 1, that means this is what? 1 plus something. If I have 1 plus
1.
something, it is 1. So that's why I got
1.
it 1. Okay. Now I have x is 1, so that means x bar is 0. So I have written 0 here. And then this is plus. Now I have z bar, I keep it here. X I substitute 1. And then it becomes 1 plus y. Okay, it becomes 1 plus y. So now what happens? 1 remains as it is. 0 plus something is become that something, that is z bar and 1. Okay, that is equal to 1. So overall your z bar becomes equal to 1. And that implies your z becomes equal to 0. Okay.
Yes, sir.
Okay. So let us start with this question. Let me type it here. Okay, this is the question. If x equal to 0 and this expression is equal to 0, then what is z or y? What is the relation between z and y? Or whether something is 1 or something. So you have to substitute x is 0. So what do we get? We have 0 plus z into y plus z plus 0 bar y, right? Into y plus 0 bar into z
Plus y.
Okay, this is equal to 0. Now 0 plus something is that something, so that's why this is becomes z into y plus z, and 0 bar is what? 1. So it is 1 into y. Okay, and this becomes y, and 0 bar is what? It is 1 into z plus y. This is equal to 0, right? So this is what? Z into y plus z plus y into y plus z plus y. This is equal to 0, right? Then what do you get? This becomes z and y plus y is
Z
y.
equal to 0.
So z
Y
plus
plus Z.
and this also is z plus y. This is equal to 0. So if you want, so if you have z plus y, so then you've got what you get? You get z and z plus y equal to 0. Now, is this 0 or is this 0? Which one will be 0? Can you tell?
Z equal to 0.
Z equal to 0.
Z equals to 0.
So you get z equal to 0. Okay. Okay, fine. So let us start with what you say. Let us go back to floating point because that is the main focus of this. The sum of product and product of sums, we will again do it in the next week. Okay, so yeah, I have not explained it well today. I'll explain it again next week. Okay. All right. So let us see this question. You have two decimal numbers, 12 and 1.25, and they are in 14-bit simplified floating point format, which is 1 bit for sign, 0 for positive, 1 for negative, 5 bits for exponent with a bias of 15, and 8 bits for mantissa, normalized with implicit leading 1. Okay. So let's do this. I think we have done for 12. Have I done it for 12 earlier? Let me see. For 12, have I done it? No, for 12, I haven't done it. So let's do. So it is floating point 12, right? 12, when you convert it to binary, it becomes 1100.00. Okay. Now, this has to be converted into that, how it should be. It should be in the format 1 point something something, right? It should be 1 point something. So it becomes 1.10000. And since you have shifted it right by 3 bits, it becomes into 2 raised to.
cube.
Okay, into 2 raised. Now, sign bit is what? Sign bit, it's a positive number, so sign bit is 0.
0.
Yes. What is your exponent? Exponent
3.
0 double 1.
And your mantissa is 100 and so on. Okay. Now you have to add exponent with bias. Bias is 15. So it is 3 plus 15. So this becomes equal to 18. Okay. Now 18 in binary, how do you represent 18 in binary? Can you write?
10010.
16.
10010.
0.
Okay, very good. So your floating point number is 0. Okay, this is 0. This for your sign. Then for your exponent, you have 10010. Then for your mantissa, what do you have?
1 0.
This one. Okay, so you have 10000. Since there are 8 bits for mantissa, you have to add remaining bits as 00. Okay, so this is the for sign number 12. Okay, in floating point. Now we have to do for 1.25. 1.25. Okay, 1.25 in binary, how do you represent it? Can you tell me?
Division.
1.25 will be actually
1 1 1 1 1 1 1 1 0 1.
1111101. Why? It is only 1.25.
0.01.
Okay. So let us write it. So it is 1 plus 0.25, right? So it is what? 2 raised to 0 plus 2 raised to minus 2, right?
1.01.
Yes, yeah. So it is actually 1.01 in binary, right? Yeah, I think someone mentioned it also, 1.01 in binary. Now, do we need to add any exponent to this? Do we need to shift the bits or something, or is it in the format we already need?
No, sir. It is already in the format.
Yes, it's already in the format. So it is 1.01 into 2 raised to 0, right? And what is the sign
Yes,
of
sir.
it? Sign bit of
Positive. 0.
So that's why you will write it as
0.
0. And then in the exponent, what will you write in the exponent? What should you write?
0.
No,
15.
0.
correct, very good. It should be 15. So
15.
15. 0 plus 15.
okay, so 15, how will you write in binary? In terms of 5 bits, how will you write 15?
1 1 1 1.
Yeah, it is
Yes,
0
sir.
1 1 1. Very
1,
nice.
1, 1.
Correct. Very good. And the mantissa, what you will write?
0, 1.
0 1. And then you will write
So on.
as 0.
0, 0.
Yes. Okay. So very good. You all are learning it. Okay. Very encouraging to see that you have understood this. So now you have to add 12 and 1.25. Okay, so this is for 1.25, and for 12, what it is? It is 0, and you have 10010. So it is 10010, and then you have 1 0 and all zeros. Okay. So can you add it directly? Can you add these numbers directly?
No, sir.
No. Okay, so what should I do then?
In Mantissa, it is 1100.
Again repeat.
110000.
11000. In which one?
Mantissa.
For which one? For 12 or for 1.25?
Some 12 plus 1.25.
Okay. The 12.25. Okay, for 12.25, we know the answer. For 12.25, the answer will be what? It will be 0 1 0 0 1 0. And then it will be what?
It is 13.25.
Oh, it is 13.25, right? Yeah, so this will be 1. And then it will be 1 1 0 0 0 0 0. This is the answer. Right, in 13.25. Right? No. It is 10010. 10010. Oh, 13.25, no? Oh, silly of me.
Sir, can we add directly?
No. You cannot add. I think that's where I made a mistake. Sorry. Cannot add directly. So what you have to do is, this is actually in terms of exponent. This is what it is. 16 plus, this is 18, and this is actually 15, right? So what we have to do is we have to make it into the common exponent. And common exponent we should do in such a way that you have to shift it. So what we make it into common exponent of 15. So you have to make it into a common of exponent of 15. 12 you have to convert it. So sign remains as it is. So this becomes 0 and this becomes 15. That means, how will you get it as?
Sorry, if we equal the exponents 2 power 4, 2 power 4.
What do you mean 2 power 4, 2 power 4?
If 1.25 is 0.000101 left, right, we have to shift right shift. The power is 2 power 4 only now.
No, I'm actually not getting
So
it.
12 and 1.25 exponent both are is same.
12 and 1.25 exponent is same.
When we have to right shift 1.25, we have got 1.01 for 1.25.
Yes.
If we right shift 2 3 times 0.000101, we have exponent equal 2 power 4, 2 power 4.
Okay. Correct. Very good. Yeah, that's what we should look for. Correct. So as who said this?
Bharat.
Okay, Bharat. So as Bharat is saying, this is more simpler to do for 1.25. So what we do is we make it as, we right shift here and make it 1.25, we make it as 10010, and this we right shift it by 3 bits. So it becomes 0012. So 1, 2, so this. This is actually how you represent 1.25. Okay?
Sir, once explain that, sir.
Yes, okay. So as we should make sure that we are representing the same exponents, okay? It is either an 18 or 15. So which one should we choose? If we make 18 into 15, then your mantissa will become greater than 1. See, your mantissa should be 0.0 something, right? Or 0.1 something. It cannot be 1 point or 2 point or 4 point something. So that's why what we do is we convert the 1.25 mantissa, we make it even more smaller. So we make it 0000100, but we take it a right shift of 3. Okay, what we do? We do a right shift of 3. Okay, since we are doing a right shift of 3, we have to add 15 plus 3 over here and make it 18. Okay, so once we have made the exponent same, then we can add it. So we have 0, 10010, and then when we add it, what do we get? We have to add these two. That is, we are adding this and this. So it becomes 10001 and then 00. 1, 2, 3, 4, 5. Okay, 6, 7, 8. Okay, 0. Okay. Is this understood? Or do you want me to repeat it again?
Yes, sir.
Yes, sir.
Okay, yes. Okay. So 1.25 we represented in exponent is 15 and your binary number is this one. Your mantissa is this one. Okay. 12, it is 0 and the exponent is 18 and the binary and the mantissa is this one. Okay.
Yes.
So now we have two options. We either convert 15 to 18 or 18 to 15. Which one is correct? Okay. Now, if you try to convert 18 to 15, you have to do what is known as left shift. You'll have to do what is known as left shift. If you do left shift, your point will go, okay, let's say 12. 12 is what? It is actually 1.1000 into 2 raised to 18 into 2 raised to 18 minus 15. This is actually a value of 12. Okay, it is 1.100 into 2 raised to 18 minus the bias of 15. And 1.25, that is actually equal to 1.0100 into 2 raised to 15 minus 15. Okay. Till this point, you have any query, any doubt, you ask me. Any query till here?
Sir, how do you write 15 minus 15?
I can write it, no, because 2 raised to 0 is 2 raised to 15 minus 15. Because the bias is 15. And we already wrote, now see, we already wrote 1.01 into 2 raised to 0, right? So 2 raised
Yes, sir, understand.
2 raised to 15 minus 15. Okay.
Okay, sir.
What I could do is I could write it as 1.01000 into 2 raised to 3. No. I can write it as 2 raised to, this I have to convert it, if I want to make it 18 minus 15. So I have to multiply it by 2 raised to minus 3. Okay. So I write 1.25 as 1.01000 into 2 raised to 18 minus 15 into into 2 raised to minus 3. Now, I'll write 1.25 is equal to 1.01000 into 2 raised to minus 3 into 2 raised to 18 minus 15. Now 2 raised to minus 3 means what? 2 raised to minus 3 means I have to do a right shift. Right? So it becomes 0.0 and then 1, 2, 3. So 0.00101 into 2 raised to 0 into 2 raised to 18 minus 15. Right? Okay, this floating point topic is a bit difficult. I think the examples also are a bit hard for you guys to understand. So what do you propose? Like, should I start one more time or do another time, or what do you want? Because I mean, I'm understanding you guys are getting stuck over here. It is becoming difficult for you guys to understand. Let us say, do you want me to restart teaching floating point once more? Or
Yes, sir.
okay. Okay, so let's start floating. Okay. Okay. So let's start floating point. We have the number. Let's take the number, simple number 8. Or let us take the number 9. Okay. So 9 is in decimal. In binary, what does 9 come out to be? 1001. This is what is 9 in binary, right? It can also be written as 1001.002. Okay, just the point, it is there for showing it. Now, this can also be written as 0001.00100 into 2 raised to 3. Is it because what I am doing? I am doing a right shift of 3. Right? I am shifting
Yes,
the
sir.
bit. So that's why I have to multiply it by 2 raised to 3 such that the value remains the same. Okay, the value has to remain the same. So I am right shifting it by 3. Now this is come in this format. Similarly, let us take the number. Now over here you can, this is your mantissa. This is your mantissa. This is your exponent. Okay, this is your exponent. Right?
Yes, sir.
And then is the bias part, adding bias and all fine? Is the adding the bias part and all fine for you guys? Or the bias part also you have query?
No, sir.
Okay, bias part is fine. All right. Now, now this 9 and 10, if you want to add it with, let us say 1. Okay, this is 9. Let us say this is 9. Let us now consider 1. 1 is what? 1.1 may be a bit too simple. Let us take 3. Okay, let us take 3. 3. This is 3. Okay, 3. 3 is what? 101. No, sorry, it is 011.
0011.
Okay, so that is what? How do you represent it as? 011.0, or it is 1.100 into 2 raised to 1. Okay, into 2 raised to 1. Right? Any queries in this point? 1.100 into 2 raised to 1. Now, if you want to add them, if you want to add 9 plus 3 That is what you have 1.0010 into 2 raised to 3. You have to add it with 1.100 into 2 raised to 1. You have to add them. Now, because you cannot add 2 raised to 3 and 2 raised to 1, you have to make it common. So what possible combination you can do? You could either make this, let us leave this 2 raised to 3 as it is. We want to make this 2 raised to 1 into 2 raised to 3. So if you want to make this 2 raised to 1 into 2 raised to 3, no. Which one should I take? 2 raised to 3 is here, 1.001. If you right shift it, then this will become 2 raised to 1. Okay. Yes. Sorry. So this will remain as it is. So this becomes 1.1002 into 2 raised to 3 into 2 raised to minus 2. Okay. 2 raised to 1, I'm writing this 2 into 2 raised to minus 2.
Yes, sir.
That is actually 1.1002 into 2 raised to minus 2 into 2 raised to 3. Okay. Then 2 raised to minus 2 means what? It means you're right shifting it. You're making it smaller. So as it is minus 2, you have to do right shift of 2. So it becomes 0.0110 into 2 raised to 3. Okay. And then we can add the bits. So then how do we add? So now our 9 is what? 9 remains as it is. It is 1.0010 into 2 raised to 3. And our 3, it has become what? 0.0110 into 2 raised to 3. Now we can add them. So now when you add them, what it becomes? This becomes 12. Right? And this becomes equal to your 0. 1 plus 1 is 0. Again, 1 plus 1, 0. This becomes 1. This becomes 1. And this becomes 2 raised to 3. Okay. And then if you add 2 raised to 3 means now you have to do the left shift. So you have to left shift by 3 points. So it becomes 1100.0. Okay, into 2 raised to 0, which is your number 12. So this is how you do floating point addition when you have these numbers. So what you have to do is basically you have to make the exponents common. You have to make the exponents common. To make the exponents common, you do all these steps to finally get the addition.
Yes,
Okay?
sir.
Okay.
Sir,
Yes.
sir, if we have a chance to add without same exponent, how can we do, sir?
No, you cannot add without same exponent. The exponent has to be same, then only you can add.
Okay.
That's why we had to go through the entire process of shifting right, shifting left, and so on.
Okay. So just it's a normal.
Yeah. See, in the exam and all, you don't need to do all this. This way I was showing what actually your machine will do. Exam, you can just add 9 plus 3 offline, you can get 12 and directly you can convert it. It will not be an issue in the exam.
Yes, sir. Yes, sir.
Yeah. Okay, so
Sir,
actually...
in the process of
Sir? Yes.
In the process of doing the same exponential, we are converting like 1 point into decimal into like 0 point decimals. No, sir, there is no problem.
Yes, there's no problem. The problem will happen when, I could have made this 9. This 9 could have been made into 2 raised to 1, right? This 9 which is here, which is what? It is 1.0010 into 2 raised to 3. That is very simple. No? We could have made it 1.0010 into 2 raised to 2 into 2 raised to 1, right? And because what do we have? We have 3 is what? Our 3 is what? 3 is 1.1. 100, right? Into 2 raised to 1. So I could have converted it like this, and I could have made it what? I could have made it 110 point. Sorry, I could have made it 100.1 into 2 raised to 1. And I could have tried adding it. That could also be a way, but that is not allowed because your number cannot be more than 1 in this point. Over here, your number cannot be more than 1. That is why you don't do this process. You keep it at 2 raised to 3, and this 3 of decimal 10, you make it into 2 raised to 3 in that process.
Okay, sir. Means it should not cross over 1.
Yes, yes.
It could be less than 1.
Yes, yes, correct. It could be less than 1.
Okay, sir.
Okay. Yeah. So actually over here, what was the mistake was, over here the mistake which I did was, I made, when I was shifting the bit.
Sir,
Yes.
sir, can you once just tell me what is truncation, rounding, and error? Just what's about it?
About truncation, rounding of error.
Yes.
Yeah, like
I have listened in last Thursday section. Last Thursday, I have listened in normal online class.
Okay.
I cannot understand it. Can you tell once what is truncation, rounding, and error?
Yeah, like truncation, let us assume you have only 5 bits, okay? And you have, let us say you have the number 1.0010, or let us say this is your format. Let us say this is your format. So this is what 2 raised to 0, 2 raised to minus 1, 2 raised to minus 2, 2 raised to minus 3, 2 raised to minus 4. So this is equal to, in decimal format, it is 1.5, 0.25, 0.125, 0.06125. This is your number. Okay. But suppose you want to represent the number 1.08125. That you cannot do. It will be rounded off to this number. Okay. So that is the round off. That is the error which is there. Because your bits are not infinite, right? You don't have an infinite number of bits. If you want to represent 1.08125, then what you'll have to do, you'll have to do 1.0001, and then you'll have to add some 1010, something like that you have to add. But if you do not have those number of bits in your computer will have either 32 bits or 64 bits. But if you need 128 bits to exactly represent the number, then you cannot do it. So it gets rounded off to a number which is close to it. Okay. That is your round off, and that is your truncation.
But in truncation, we have to remove last 2 digits of the point. No, sir. If 1.08 is a number, we have to remove 125.
No. Why your number is 1.08? You wanted it to be more accurate, right? You wanted to make 1.08 125 assume. So then you have to go through that struggle.
8. So if the number is 1. If we have to got 1.06.
No, if
1.06 125 is the original number.
No. I'm saying let us say your original number is 1.08125. Okay. This is your original number. Okay. But your resolution which you have is 0.06125 only resolution you can have. Okay. This is your resolution. Okay, this is your resolution. So that means you can have 0.06125, or you can have double of it, or triple of it, or 4 times of it, but you can only have in terms of 0.06125. But your 1.08125 does not come in terms of that. Okay. So that is why you bring it to a number close to it. So the closest number which I think you can get is 1.06125. Or let us say you can get another number. Let us try adding the resolution over here. So that will become 0, 1. There is 5, 2, 2, 1, 1. Okay. So the number which you could get is 1.12250 or 1.06125. These two numbers only are possible. But your actual real number which you wanted was 1.08125. So the closest number, the number which is closest to this is this one. So you will select that number, your processor will select that number when it will do your representation and everything.
Okay.
Yeah.
So, but in rounding rules, after decimal point, we have only 2 digits only.
Why?
I don't know, but it's just having rules after decimal, only 2 numbers we have to place.
No. That's not the rule. That if that is there, then how will you do all these big divisions and all that? It's not the rule.
After, if we have 1.06, the
Huh?
rounding number will be 1.07.
Why?
That's only I don't know, sir. If 0 to 4 after decimal point, after the decimal point 0, 2 numbers before we have to 0 to 4, we have no change. It is unchanged. But if we have 5 to 9, we have to change the next number. We have to change to next number.
Achha, that is your round off, which you do in the general sense. But this round off, which is there in your digital circuits, is different. Like, let us say, if you got marks, if you got, let us say, 12.25, right? Then what the teacher will do, 12.25, she will make it 12 marks, right?
Okay.
But if you got the marks of 12.75, she will make it 13, because she has to round it off to integer numbers or something, right? But in your decimal thing, in your circuit, you want 0.00 something also. So that round off is different.
Okay.
Okay.
In binary, if it is given in binary,
Yeah, in binary, you do not need to represent to 0.02 or 0.01. You might have to go to 0.000001 also. It is fine. It might be possible also. But that depends on the number of bits which you take.
can you give an example for binary?
Binary, like, suppose you have 1.00000001. So what is this? It is 2 raised to minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 6. It is 2 raised to minus 8. So this number is what? It is 1.2 raised to minus 8 is how much? Does anyone have calculator? Hmm?
0.0039.
0039.
2 power minus 8.
Yeah, there'll be some more numbers, no? 0.0039 what?
39600625.
Yeah, that's all. So this is your number. Okay. Yeah. But now, if now what happens, you have only this many number of bits. Suppose you have only this many number of bits. Then you might leave it as 1.000 only. So then your number 1.00396025 gets rounded off to 1. Okay, that is like your round off.
Okay.
Yeah.
Okay.
Okay, so I actually realized one mistake which was made over here. So this 1.25 which is over here, when it is being converted. No, which one was that? When this was being converted, this is 1.25 you're converting, it will actually become where it is. It will, sorry, please don't write here. It will be 101 over here. 101 over here. Because it is actually 1.0100 and you're right shifting it. So when you're right shifting it, it will become 0, 0. You're right shifting it by 3, so it will become 0, 0. What it becomes right shift by 3? 0, 0, 1, 0, 1. 1.01, so 0, 0, so 0, 0, 1, 0, 1, correct. Right. So when you will add it, when you overall add it, it will become 0, 0, 0, 1, 0, 1, 0, 1, and you have 0, 1, 0, 0, 1, 0. So this is your 13.25 is actually represented like this in this representation. Okay, so that was the mistake I made. That's why it took lots of time. Okay. Okay, so do you have any more queries or should we end the session? Okay. So if there are no more queries, then I'll end the session. Okay, so thank you for joining. This recording will be uploaded on YouTube. Okay.
Thank you, sir.
Thank you.